Hello, ladies and gentlemen. Today we are going to do section 12.7, similar solids. And this is actually our last lesson in chapter 12. So we're going to determine whether two solids are similar. So this is going to be very much in line with what we did with similar polygons and similar triangles and so forth. So we're going to tell whether two solids are similar using the same strategies we have done before. So, similar solids, two solids of the same type with equal ratios of corresponding linear measures. That's what similar solids are. So in other words, two solids are similar if and only if all their linear measures have a ratio of A to B. So the side, just like before, the sides have to be in a ratio of A to B. And that can be whatever you're given. It could be the heights, the radius, diameter, slant height, circumference, perimeter. All of these right here will have the same linear ratios of A to B. So if we want to tell whether the pair of solids is similar, we compare. We compare the smallest side to the smallest side, the linear measures, 4 to 3. We compare the largest side, 16 and 12. And we compare the in-between side, or the corresponding side, of 12 to 9 to see, are these all the same ratio? And all of these they all reduce to 4/3. And remember, if they're bigger fractions and you're not sure, you can also check by dividing the numerator and denominator and see that these are all 1.3 repeating. So yes, these are similar. So if we want to tell whether these are similar, we look at what corresponding linear measures are given. Well, we have this radius here of 4 and 12. So we see if 4 to 12, is that going to be corresponding to either this height right here, or which we don't have over here, or the slant height right here, which we don't have over here. So what we can do is we can use the Pythagorean theorem to find this slant height right here. So, and then we can compare that. So we would take 6 squared plus 4 squared and set it equal to our slant height squared, and that is 52. So our slant height is the square root of 52. So that means the square root of 52 over 18 is supposed to equal. And I think it's obvious, but again, you can get decimals for these, 0.3 repeating, and this is 0.4006, so these are not similar. So look at the linear measures you're given, write it in corresponding ratios, and see if they are the same. If they are the same, they're similar. If they're not, then they're not. So let's take a look at surface area and volume and how it compares. So these two are similar. These two are similar solids because all of the corresponding 1 to 2, 1 to 2, 1 to 2. All of the sides are in the ratio of 1 to 2. So my edge length here is 1 and my edge length here is 2. My surface area of this cube right here is the area of the base, so 1. So we have the area of let's just write this down, the area of the base times 2 plus the perimeter of the base times the height. That's what it is for prism. That's our surface area. So the area of the base is 1. Multiply that by 2, we get 2. The perimeter of the base is 4 times the height, which is 1. So we get 2 plus 4 is 6. So let's find the surface area of the larger cube down here. We have the area of the base, which is 4. Whoops. We have the area of the base times 2, so we have 4 times 2 plus the perimeter of the base times the height. Perimeter of the base is 8 times 2, so we get 4 times 2 is 8, plus 8 times 2 is 16, And 8 plus 16 gives us 24. And the volume. The volume is the area of the base times the height. So we have the area of the base, which is 1, times the height, which is 1. So we get 1. And that's 1 cubic unit. And for the volume of the larger one, we have the area of the base times the height. So we get 2 times 2, which is 4, times the height, which is 2, which is 8. So if we look at the ratio of the side lengths of these similar solids, it's 1 to 2. If we look at the surface area, it's 6 to 24, but that reduces to 1 to 4. And if we look at the volume, it's 1 to 8. And so this falls right in line what we did with similar polygons and the area. So if our ratio of sides is A to B, notice our area, in this case surface area, is A squared to B squared. So 1 squared is 1 and 2 squared is 4. And the ratio of the volumes end up to be A cubed to B cubed. Maybe like you would expect, okay? So that just sort of models that for us, and then this is the actual similar solids theorem. If two similar solids have a scale factor of A to B, then their corresponding areas have a ratio of A squared to B squared, and their volumes have a ratio of A cubed to B cubed. So this is kind of the important pieces. Above, it's just written out the same way with some solids highlighted. So this shouldn't be too difficult. We're just adding from side ratio, area ratio, which we already know, to our volumes. So look at what you have and then write the correct ratio and use the correct proportion. So let's try working out a problem. It says the solids below are similar. Find the surface area and volume of the second figure. Okay, so if the solids are similar, then we know the sides are in the ratio of 4 to 7. So that means the surface areas are going to be in the ratio of 4 squared to 7 squared, and the volumes are going to be in the ratio of 4 cubed to 7 cubed. So to find the surface area, I take 4 squared, which is 16, over 7 squared, which is 49, and I could write those in, or I can just use those values in my proportion. And I set it equal to the surface area of the smaller ones, because this is the smaller and this is the larger. So now I need to write the surface area of the smaller, 74.24, compared to the larger, which I don't know. And then literally I just cross multiply, and that gives me the surface area. The larger one is 227.36 centimeters squared. Now I'll do the same thing with volumes. To the small to the large is 4 cubed over 7 cubed is going to be in the same ratio as the volume, 37.33 over y, call it x or y. And again, cross multiplying, that gives you a volume of 200.07 centimeters cubed. So just use the linear ratio of sides or any linear measurement, whether it's a radius, could be a height, a slant height, could be a perimeter, could be a circumference. Use any sort of linear side ratio and then square it if you're trying to find surface area, or cube it if you're trying to find volume. Now, if you're given a surface area or volume ratio, then you're going to have to scale it back. So this one says two solids are similar. Find the scale factor or the ratio of the sides. So it's giving us our volumes right here. So we know our volume ratio is A cubed to B cubed. We know that. So we write our volumes in there, 432 pi over 2,000 pi, and now we reduce it. Well, we can cancel out the pi's, okay, because that is a common factor. And then we have 232 over 2,000. Well, I know I can cut them in half, so that's going to give me 216 over 1,000. I can probably keep cutting them in half, but I notice that this is equal to, again, our a cubed and our b cubed. So how do I find what number times itself 3 times equals 216? I'm going to need to take the cube root. So what I do is I take the cube root of each of these, which gives me 10 over here, and it gives me 6 right here. So my side ratio actually is 3 to 5. Another thing you could do is you could probably, I would just try to take the cube root of something that you recognize. All right, so that's kind of the basics. I would do your best to work through several different kinds of problems, even though you're deciding how many or which problems you want to do. I would try to pick out 15 on this so that you're practicing a whole bunch of these ideas to kind of get this down. This is our last lesson, and I will host a Zoom session either tomorrow or Monday as we get prepared to test on Chapter 12. Have a great day.